This talk is about our SnapperGPS project. With SnapperGPS, we aim to develop an open source GPS receiver with very low energy consumption and at very low costs, mainly for wildlife tracking. So our current version here that can basically run years on just a single coin cell while using pretty simple hardware to keep the costs down. And our paper here at SenSys is mainly about the fast and robust positioning algorithms behind SnapperGPS that allow you to still get an acceptable accuracy of about 11 meters in real-world applications from the very, very rough data that this receiver spits out. But I think at first I need to provide some background. So global navigation satellite systems like the GPS, they allow us to localize objects, humans, or animals anywhere on the Earth. For example, biologists tag wild animals with GNSS receivers to track them and to learn about their behavior. However, traditional receivers have disadvantages in this scenario. So a traditional receiver decodes the satellite signals and compute locations on the device in real time. So the signal acquisition and processing is computationally quite expensive and also needs lots of energy. And if you run them on a battery, then the lifetime is quite limited and they are bulky because you need a large battery. And those traditional receivers, they also need from time to time a longer visibility of the sky. And that can be kind of a challenge when you track a marine animal that surfaces only briefly. And the energy consumption I just mentioned, that's also a problem for like other applications such as fitness tracking or low-cost logistics tracking, at least certain types of it. So, and then there are snapshot receivers, and they basically address all the challenges that I just mentioned. Snapshot GNSS receiver would just sleep most of the time, and it only wakes up at defined intervals to record short snapshots of satellite signals. And these receivers, they do not process the signals on the device. Instead, they digitize raw signals and just store them. And after you recover such a receiver, you transfer its data to another computer, for example, in the cloud. And that computer then estimates the receiver's position history. And this procedure basically eliminates any onboard signal processing, as well as any real-time data transmission, which together greatly lowers the hardware complexity as well as the energy consumption. So a few snapshot GPS implementations have been presented in the literature so far, but several aspects are missing. For example, most of them have just been evaluated in simulations or on data from commercial GPS front ends that provide pretty good signal quality. However, you really want to build like tailored, simplified hardware for this to benefit from the low energy consumption and the low costs that this snapshot technique in theory allows. So existing implementations, for example, require relatively high sampling frequencies, of often like at least 16 megahertz. And they also want like several bits for the amplitude quantization of those captured snapshots here. And instead, our SnapperGPS receiver uses a much lower resolution, just 4 megahertz sampling rate and 1 bit amplitude quantization. And this does not only reduce the amount of required onboard memory to store the snapshots, it also allows to capture the snapshots with the USART interface of a cheap, low-power microcontroller that runs at 16 megahertz. And altogether, this simplifies the hardware, which again reduces costs and energy consumption. For example, with hourly fixes, this SnapperGPS receiver consumes just about 15 milliampere hours per year. However, as I said before, existing snapshot GNSS algorithms are not robust enough to provide reliable, accurate, and fast positioning based on these ultra-low resolution signals that are captured by our SnapperGPS hardware. So our goal here is to develop improved or even novel snapshot positioning algorithms that significantly increase accuracy and reliability for these signals. And for this, we use probabilistic signal processing But I think at first I need to talk a bit about the traditional approaches to snapshot GNSS. So for this, let us go back to our snapshot GNSS workflow here. So the main problem is that the cloud segment here must estimate locations from very, very short signal snapshots. In our case, just 12 milliseconds. And these are way too short to decode like any payload data. For example, signal transmission timestamps. So it doesn't know the timestamps, it also does not know then the signal travel times, and hence also doesn't know the distances to the satellites. In consequence, we kind of must reconstruct the timestamps from the raw snapshots. And for this, we have to rely on the unique periodic codes that all the satellites broadcast. They have period lengths of like 1 to 10 milliseconds, which basically corresponds to about 300 to 3000 kilometers. And what we do is we specifically look on the so-called code phase. The code phase is the shift between the start of a new code period of a certain satellite signal and the start of our signal recording. And this provides some information on the signal travel time. So to be precise, the code phase is the last fraction of the signal travel time. So let's say you can fit n.x codes between you and the satellite, then you wouldn't know the integer n, but the code phase tells you the last fraction x. So you can basically exploit this in two ways. The first approach comprises two steps that are called satellite acquisition and course time navigation. Satellite acquisition estimates the code phases for each potentially visible satellite from the raw snapshot. And course time navigation then reconstructs the full distances to the satellites and estimates location and time. However, as I said before, existing implementations use non-robustly square optimization for the latter, which prohibits using very low sampling rates and amplitude resolutions, where you might have lots of outliers here. So our first approved approach to snapshot GNSS builds on a tailored acquisition stage and then uses Bayesian strategies to efficiently and robustly identify and remove the outliers that the acquisition stage provides. For this, we put priors on each satellite observation and use an algorithm that is inspired by the RunSAC algorithm that is often used in computer vision. We quickly test different subsets of observations and use basically until we just found one that is plausible. And then we also incorporate all the other satellites whose code phases approximately agree with the solution from the tested subset. In this way, we increase the accuracy by incorporating more observations. However, unlike for the standard RunSAC, we don't just randomly select the subsets. Instead, we select them guided by their prior likelihood to be reliable. And yeah, we also implement like an alternative to this traditional approach. We have a novel second approach which uses maximum likelihood estimation instead of the least squares optimization here. And what we basically do here is that we model the code phase observations as a mixture with normally distributed valid observations and uniformly distributed invalid measurements. And in this way, we basically jointly solve the outlier detection problem and the final positioning problem in a single probabilistic framework. And here we also use maximum likelihood estimation to estimate certain error parameters of our locust hardware at first. For example, the frequency offset of the front end. That can be quite large, and knowing this significantly increases the speed of the satellite acquisition. So, and in addition to course time navigation, there's also a third approach in the literature to snapshot GNSS, and that one does not separate snapshot GNSS into acquisition on the one hand and course time navigation on the other hand. Instead, it's called direct position estimation, or just direct positioning, or collective detection, which are basically three terms for the same thing, and they all have just a single step. we basically directly estimate the position of the receiver that maximizes the likelihood of observing the captured raw signal. Basically, you compare the signal that you would expect to receive at a certain point on Earth with the signal that you actually received. And for the optimization of this likelihood, we take an existing algorithm that is based on branch and bound optimization, and then we take it and tailor it to low resolution signals, such that it runs faster and is more robust. Specifically, we integrate over consecutive code periods in the snapshots to increase the signal to noise ratio. And then we also use more than just one satellite system. And we investigate these three concepts to determine which one is best suited for ultra low resolution signals. 4 MHz sampling rate and 1-bit amplitude quantization, as I said before. So let me just say that we also provide like implementations of all of them as like an open source snapshot GNSS algorithm compilation on GitHub. And we do a real-world evaluation of all those implementations where we have moving low-cost receivers in quite diverse environments. And below you can see some empirical cumulative distributions of the resulting horizontal tracking errors using different numbers of satellite systems and hence satellites here. And we basically show that our outlier detection methods improve the success rate of course time navigation from 81% to 97% and reduce the median error from 50 meters to just 12 meters. And at the same time, the algorithm runtime increases by only a few percent. And this accuracy, 12 meters here, that is sufficient for many applications, for example, wildlife tracking, and our novel maximum likelihood estimation algorithm, the second one from the previous slide, that has an even better accuracy of 11 meters. Unfortunately, its runtime is 3 times higher, but still pretty low. And then finally, our modified direct positioning algorithm achieves the same reliability of 97% while using less satellites. But unfortunately, the runtime is like magnitudes higher. However, this is like still an improvement over state-of-the-art direct positioning, which is shown down here and can only calculate fixes for 24% of our data. And just let me say, in general, like this evaluation here is the first performance comparison of like different snapshot GNSS algorithms on the same data. And we also made the data set that we have here is like thousands of signal snapshots available to the public for anyone to use and study. Yeah, so to summarize, we have a purpose-built snapshot receiver and we developed novel algorithms that allow us to operate it with an unmatched trade-off between costs, energy consumption, and performance. The whole thing is accessible via like a public web application and a cloud service that we implemented. And after we submitted the paper, we even went on to track some sea turtles here in the Atlantic using our SnapperGPS. Okay, so that's it. Thanks for your attention. It was nice to have the chance to speak here and to present our project. And since I have a few minutes left, I think I'm just gonna head over to our public website and show some of our tracks. So here, for example, I've just been cycling and walking around Oxford. So each of these dots is like a processed snapshot. Each snapshot is processed independently, no filtering here, and also no like cherry picking of the snapshots. And yeah, the environment is quite diverse. So if you go to the city center, the uncertainty of the estimate, which is the radius of the circle, gets larger because the roads are narrow. Or if you then move outside of the city, then you have like open fields where the uncertainty is lower again, or it even works in like forests. Slightly higher uncertainty, but anyways, it's quite robust. So over here, for example, we get like fixes for 99.8% of our data, which is quite nice. And I think I can also show like one of our turtle tracks. So here, basically, whenever the turtle surfaced, you got like a dot on the map. Yeah, this turtle here, that was one quite active one. as you can see. Yeah, not much more to say about this. You can also use like this website to configure a SnapperGPS receiver just from your browser using web USB. So it works in any device, no driver installation needed. And you can also download the website as like an app on your phone. This is basically just to make SnapperGPS accessible to everyone, even if they are not a technology nerd. Yeah, but I think now I shall finally give you the chance to ask some questions. Thanks again.